Today we're going to talk about so-called filtered equations. What I mean by that? Technically speaking, we could just solve using a finite difference approximation or finite volume approximation or others, just full incompressible system of equations, and that would be fine. The problem is that if we use explicit schemes, and that's basically sometimes only our choice when we're talking about three-dimensional flows, or only practical choice, we are limited by stability criterion on the time step. I've shown in one of previous lectures that for compressible equations, the stability is determined not only by advection velocity, the velocity of wind, but also sound waves. Sound waves, generally speaking, have very little or no meteorological significance. However, they are fast, and our stability criterion based on sound waves speed would be very restrictive, obviously, with a speed of about more than 300 meters per second. Your time step would be unnecessary short, because you're not really interested in sound waves. What we're interested in a basic flow, in other waves like gravity waves that have much slow speed, or Rossby waves and stuff like that. So presumably you would like to filter those waves out. But how you do that? You can of course use some, filter and in time to get rid of those sound waves, but in the process you may actually get rid of or severely distort other waves, like useful waves, like gravity waves and other. So that's not a plausible approach. So instead, what people have done, they actually modified the original equations, original differential equations, so that they don't support sound waves any longer. And this is what we're going to talk in this lecture. So let's first start from our compressible equations. Let's remember them. So compressible equations So first equation for momentum. It's du, we use wind, dt, plus I will write them in a vector form. I hope that you're familiar with vector form of equations, of momentum equations from other classes. So plus 2 omega vector product u, where omega is a rotation vector of the Earth. So this is Coriolis force, plus 1 over rho gradient P, pressure gradient force, and minus G equals to 0. So this is inertial force. This one is Coriolis force. This is pressure gradient. Force, and this is gravity. And of course there is also friction. There is friction but for simplicity, let's omit it here. So those equations without friction are called generally Euler equations. Okay, so another equation, so this is one equation. Second equation, we need, it's a continuity equation, which is for compressible system looks like the following. The rho dt plus divergence of rho u equals to 0. So this is continuity equation. And then we need some another equation. We have unknowns u, rho, p. So we have two equations right now. So third equation we can add equation of state or ideal gas equation. I mean, atmosphere is very well described by ideal gas. So P equals to rho RT. And finally, we need some energy equation. And for that, we can use first law of thermodynamics. So let's assume that there is no heat, so it's a adiabatic process. So then we'll write that Cv dt plus P d1 over rho, so it's P dV, specific volume per unit mass, equals to 0. This first law of thermodynamics, adiabatic form. So we assume that for simplicity here we don't consider any moist processes. So for this you have that Cv dt plus P divided, so it's minus here, minus rho square d rho dt. Now from continuity equation equals to 0. From continuity equation you have, if you write this as the following, that d rho dt plus u times gradient of rho plus rho divergence of u equals to 0, in the same form. Or this guy combined with this guy is actually d rho dt full derivative plus rho gradient, I mean divergence of u equals to 0. So from that you have 1 over rho d rho dt equals to minus divergence of u. So we use this one in here, which we, if we substitute this 1 over rho d rho dt here, then we will have our third equation that I just will write. Fourth equation as Cv dt plus P divided by rho divergence of u equals to 0. So now we have 4 equations and 4 unknowns. So the thermodynamic equation, equation of state, continuity equation, and momentum equation. So this is a full set of compressible equations. And this set can be used to solve basically more or less precise, assuming that atmosphere is ideal gas, of course. We can solve any problem. And not only for atmosphere, for any kind of flow, like including supersonic flow, for example. So this system contains sound waves. And these sound waves are, as we derived before, and you can actually do it by linearizing the system, like ignoring this term, ignoring gravity, so just only pressure gradient term, and you linearize it. And also continuity equation, linearized one, so that advection of density, you ignore advection of density, just remains d rho dt, local derivative d rho dt, and gradient. So the system like that, this linear system of equation, let's say some rho naught, some constant rho, linearized, gradient of pressure equals to 0, and d rho dt plus rho naught gradient divergence of velocity equals to 0. And then you use the rest of equations, or in this case you use adiabatic, like P divided by rho in power of kappa Cp over Cv equals to 0. And using those, we showed that this system, these equations produce sound waves. Sound waves with speed Cs equals to square root of R of rho RT, kappa RT, sorry. Cs equals to square root of kappa RT. So speed of sound, it's only a function of temperature. It does not depend on density. So everywhere in atmosphere, if even near the surface, if temperature is say 0 degrees Celsius, and in stratosphere when it's 0 degrees Celsius somewhere, speed of sound is the same, even though air there much less dense. Okay, so you see which terms produce sound. So this term mostly responsible for producing sound. D rho dt, change of density, adiabatic change of density, and also interacting with this term, with pressure. So these waves are pressure waves. Okay, so this system of equation would have sound waves, unfortunately. And then our stability criterion would be something like current number equals to C or U, this maximum of U plus speed of sound divided by delta x times delta t should be smaller than, well, for most schemes, like about 1 or in the order of 1. Depends on particular scheme. It can be actually for, say, it depends on time scheme you use, like for Adams-Bashford, for example, scheme, it could be something like 0.7. For other schemes, it can be 1. For, say, Runge-Kutta 4, it can be like 2. But it's all kind of very limited, and it's limited by this speed of sound, which has again no meteorological significance. So this system would make sense to solve when you say simulate flow in a rocket engine, for example. Then all this flow is very close, or it may exceed Mach 1, so it's supersonic, and it's, of course, you need to use compressible. But in meteorological applications, we don't really need any of that. So we need to formulate some system of equations that actually don't have speed of sound. So this is a canonical form that some people actually use to model atmospheric flow. But there are other approaches to the same compressible flow, that compressible equation, that actually don't use this particular set of variables, and we'll talk about that a little bit later. So now let's, so we have this problem with this guy. So this is compressible equations. And for these compressible equations, you can actually derive conservation of energy equation. I'm not going to derive it here. Maybe I will give it you as a homework. Basically, what you do, you multiply this equation. To get the equation for kinetic energy, you multiply momentum equation by rho u. So multiply 1 by rho u. And it's easiest to get rid of this term is actually to write this equation in so-called vector invariant form, which looks like the following. So in this vector invariant form, you need the following. You can replace this pesky term that is difficult to, when you multiply by rho u, to show what you want. Instead, if you do this term is actually equals to this. So vorticity, vector product of vorticity, vector product of vorticity and velocity, and plus gradient of kinetic energy. So you replace this term with this, and then if you multiply it by rho u, you see that because this is vector product with u, and you multiply, you not vector multiply, you multiply it as a scalar product, of course. And scalar product of u times this vector product that involves u itself means that it's 0, right? It's because a times a vector product of b equals to 0. That's just from basic math. So you will get rid of this term. So this term is not participating in your equation. Now another thing that you use, and of course Coriolis term also will disappear. So Coriolis term obviously does not produce kinetic energy because of that, because if you multiply scalar by u, you see it contains u itself vector, so it will cancel. It will disappear. And another thing that you need to use is just that you need this fact that you can easily derive, that's easy to derive. Why I'm explaining all this? Because it may be on your homework. It's the rho dt, d phi, any variable phi equals to d phi dt plus u times gradient of phi. It's actually equals to d. So now if you multiply it by rho, and then you can show that rho d phi dt actually equals to d dt rho phi plus d plus divergence of flux. We actually showed that when we consider conservation properties of transport schemes. So it's divergence of rho u phi. So this is another thing that you need to know. And if you do that and you multiply this by a rho u scalar product, and also this is a little bit tricky, guy. You need to also do you need to show that, well, I'm not going to talk about that here, and then you'll combine with thermal energy or with internal energy. So then you can show you can derive the following conservation equation, that the total energy, which is defined like this, total energy equals to rho u square over 2, so this is kinetic energy, plus potential energy of one specific kinetic potential energy, so it's rho gz. So kinetic energy plus potential energy plus internal energy, CVT. Then there is conservation, that dE dt plus divergence of flux as E plus P. So flux of total elastic energy. So it's basically this energy, total energy plus P times U equals to 0. So energy is conserved. So when you integrate it over the whole domain, you know that integral of divergence, if you have periodical domain, it will disappear, as we showed in the conservation, when we discussed conservation properties. Then the total integral of energy is conserved. So the bottom line, that compressible system of equations is basically exact in a sense that, well, it has this very known conservation of very known energy, which is kinetic energy flow plus potential energy of a parcel plus internal energy of parcel. So all this total energy of parcel is conserved. Of course, for moist processes, we should add there also some moist variables, but we're not going to do it here. But believe me, it's relatively straightforward to do, to extend this system to moist processes. So that's it. So this system is state of the art. I mean, not state of the art, well, this system is known a long time ago, but this is exact. So now we don't want exact because of sound waves. So let's first consider, before we before we're moving to next approximation, let's first consider what's the ultimate approximation that doesn't have sound waves. It's incompressible flow. So it's incompressible. So let's assume that fluid is incompressible. It doesn't mean that it doesn't change in space. Its density does not change in space. It can be like dense fluid near the bottom and lighter fluid above. So there is maybe some gradient, so it can start mixing and so on. But what incompressible means? Incompressible means not that the rho dt equal to 0. Not quite. The rho dt equal to 0, it means anelastic, but I'm kind of preempting. But incompressible, it means that the full derivative of density equals to 0. So d rho dt equals to 0. So this is main thing that actually make it that manifests itself as incompressible. So then there are of course no sound waves, because sound is actually the slight compressibility of fluid. This is what actually making sound. So from that it follows immediately that divergence of u equals to 0. This is from continuity equation. This continuity equation, if you write it in the form I wrote it before, then this one. So these two equations is actually continuity equation now divided into two equations. One is that d rho dt equals to 0 and then divergence equal to 0. Now we cannot use equation of state because it doesn't make sense. Any ideal fluid, ideal gas law, it's of course ideal gas, of course it's compressible. So we cannot use that anymore. So no equation of state. So now momentum equations are basically remain the same because there is nothing really there that actually would be different. All terms there will remain. So momentum equation is the same. So same as for compressible. So this is another equation. So now we have and of course there is no thermodynamic equation, which is it's also kind of requires compressibility, and we don't need it because all the information is contained in these three equations because we have only three unknowns. It's u, rho, and p. P is still in momentum equations. So we have three unknowns and three equations. No temperature. For incompressible flow, temperature is irrelevant. So how we solve it? Because, okay, for rho we have prognostic equation, the rho dt equals to 0. We can use our transport equation for that, find a different representation of that. Normal equation for momentum, we can use our, like, find the differences or find that volume for this equation, so it's also prognostic. But there is, the problem is there is no prognostic equation for P, for pressure. In our compressible system, we didn't need it because as long as we know T, prognostic equation for temperature, and density, we can use equation of state to compute P. And then substitute it, use it in momentum equation. Here we cannot do that because there is no temperature equation, there is no equation of state. So how we obtain P in order to use it in momentum equation? Because here it's still this term, it's still there. For that, we need to use non-divergence equation. So you see there is no divergence. Divergence equals to 0. For that, we basically just, let's say that momentum equation can be written like the following, in just some general form, as sum A of u. So all terms, but except for pressure gradient. And then we use pressure gradient here, 1 minus 1 over rho gradient of pressure. So this is our momentum equation. And so now, in order to use continuity equation, what we do, we find divergence of this equation. So we have d dt, and because it is partial derivative in time, and here are partial derivatives in space, they can be switched, their order can be switched it can be done only with partial derivative, as you know. It cannot be done with full derivatives like dt, like this one. But with partial, it can be done. So it's d dt of divergence u. We just switched. Equals to divergence of A, this vector, and minus divergence of 1 over rho gradient of P. So what is this? This is basically Laplacian. So it's elliptic equation. So, and this guy now, because of divergence equation, it's equals to 0 because of this equation. So now we have elliptic equation. Elliptic equation for pressure. And we need to solve it with some appropriate boundary conditions we're not going to talk about here. But that's why we needed in one of the previous, I think it was previous lecture, we talked about elliptic equations. So that's what you need now to use. So this is basically Laplacian. And so you need your iterative procedure, some iterations, unless if rho is constant, then it's even easier than it's just pure Laplacian. So you need to use your iterative procedure to solve it. And after you solve it for P, you use it in a momentum equation. And that's it. So that's what you do with incompressible flow. Yeah, but we may actually, so we may generally use only these equations, it's fine. The only problem that maybe further simplification is if we look at momentum equation, we see these two big terms. This is pressure gradient terms and gravity. And for fluid in a rest, it's some kind of basic state. Let's say we're talking about atmosphere. Atmosphere is very close to hydrostatic balance, as you know. And even inside clouds, like when you have strong updrafts, the deviation from hydrostatic balance is very small, actually. So overall, atmosphere is very extremely well described by hydrostatic balance, at least pressure field. And it's a difference between these two large terms that what makes non-hydrostatic motions, like vertical development of clouds and so on. So we can make another simplification by subtracting this hydrostatic balance from the equations. But we cannot just, if we just subtract it like that, of course that's incorrect, because that deviation from that balance is what drives the motion in the vertical. And so we need to retain some terms that only responsible for this deviation from hydrostatic balance. And this approximation for incompressible flow is called Bouusinesq approximation. So let's yeah, this board is too small, fortunately. Okay, so Bouusinesq approximation. That's very important approximation in our field, and not only in our field, generally in engineering and in ocean modeling. So Bouusinesq approximation. Bouusinesq is a French mathematician who first came up with this approximation to the earlier equations. So basically, that's what it does. So it says, okay, we have first equation we have as our like a non-divergence equation. So this is like from incompressible, and then we have d rho dt equals to 0. So this is retained. But what it actually does, it's subtracting this hydrostatic balance. For that, let's consider hydrostatic balance first. So 1 over rho gradient of P equals to G. Well, I write it in vector form, but of course it's only valid this hydrostatic balance in the vertical along the z-axis, but I will write it in general. So for hydrostatic balance, we consider that our variable, that there is basic state. So basic state is such that pressure equals to pressure, this basic state pressure, which is function only on height. This pressure, basic state pressure, is assumed to be in hydrostatic balance, plus some perturbation, which can be function of x, y, z, and t. So we replace, so P is just, and we also assume that perturbations of pressure, well, much smaller than P, than as basic state. And also we use densities also given by basic state plus perturbation of density. And important thing that for basic state there is hydrostatic balance. Hydrostatic balance. So now we can let's write these two terms as the following. So now let's substitute these definitions in there. We have 1 over rho mean plus rho prime times gradient of P bar plus P prime equals. Now let's do it like this. It's rho, take rho out from this. It's 1 plus rho prime over rho bar gradient P plus P prime. So it equals to, so this thing, because rho prime over rho is much smaller than 1, because of this, so rho prime over rho bar equals to some epsilon, is much smaller than 1. Then from calculus rule we know that 1 divided by 1 plus epsilon is approximately equals to, when epsilon is small, is 1 minus epsilon. So we have 1 over rho bar, 1 minus rho prime over rho bar, gradient P bar plus P prime. So now let's multiply. Well, I forget this minus G, but I will not write it now. I will write it at the end, so not to carry it around. So let's do it. It's 1 over rho bar gradient P minus 1 over rho bar rho prime over rho bar gradient of P prime bar plus 1 over rho bar gradient of P prime and minus 1 over rho bar rho prime rho bar gradient P prime. Okay, so now because these guys are small, so primes times prime we won't consider, it's called linearization. So basically you ignore all these binary terms or this kind of products of perturbations. So it's approximately 0. Get rid of it. Now this guy, and now let's write it minus g. So this guy, I mean this equation, hydrostatic balance, it's this guy and this guy. So they will cancel each other out. So what is left is these two guys. And now this guy divided by rho, it's actually g. So this divided by this is g. So it's equals to minus rho prime over rho bar g. And plus 1 over rho bar gradient of p prime. So this is what our these two terms in momentum equation look like now in Bouusinesq approximation. Now we can actually make it even simpler by assuming that our rho does not in the vertical does not really change much. So that we assume that our rho bar is approximately some rho naught, which is constant. So this is reference pressure, reference density. And it's done just for because this Bouusinesq system is used for sometimes for analytical, so that's just to remove this dependence on height. And besides, indeed, density, this even mean density, say in places like boundary layer, in a lowest 1 kilometer layer of atmosphere, does not really change much in the vertical. So you can ignore this change in this kind of, when you divide by it. And so you approximately can write it as rho prime. So it's rho minus, but this prime is computed with respect to the, not to rho naught. It's sometimes people make this mistake in their models. This one is computed with respect to reference profile. Not to reference density, but to reference profile of density. But you can divide it by reference density. That's fine. It's not really going to change much anything. Plus 1 over, and here we also do the same thing. Replace this dividing by this bar by dividing by rho naught. And so this is times g. Yeah. So now let's introduce. So now this equation. So we have now. Let's introduce buoyancy. Buoyancy B. Buoyancy. So equals to this guy, rho minus rho mean divided by rho naught times g. So if it's, well, of course it's acting only in the vertical because g is only in the z direction. And then this equation can be written as d rho dt equals to d dt of rho bar plus d rho prime dt. So now d rho bar, this is one and only function of z, of height. So it will be d rho prime dt plus w d rho dz equals to 0. So this is our equation for density that we replace by this equation. And now, using this definition, which is this one is just rho prime divided by rho naught g, we have equation for, we can replace it by equation by divided by rho naught, which is just a number, it's a reference density. That's why we needed it instead of a profile. Then it's just dB dt plus w 1 over rho naught d rho dz equals to 0. And what is this thing? This guy is Brent-Weissala frequency, n square, nb. It's Brent-Weissala by, I don't know exactly how it wrote, but it's basically oscillation in gravitational oscillations frequency given a profile of density. Brent-Weissala frequency. So now our Bouusinesq equations are written as so instead of, so this one is still valid, divergence of u equals to 0, and then we have dB dt plus w. This basic this guy plus w n Brent-Weissala frequency squared equals to 0. So and so this is our buoyancy equation and momentum equation where du dt plus all these terms, and instead of this pressure gradient terms minus g, you have plus 1 over rho naught gradient of p prime and buoyancy, which is like minus b minus b. It's vector because g is a vector. Yeah, it's capital B equals to 0. So we have three unknowns, u, b, and p prime. And we so we have three equations and three unknowns. But again, we don't have prognostic equation for pressure as we discussed before. So we need to again use this equation to produce elliptic equation for pressure and then solve it separately. And when you solve it, then you can substitute in here in momentum equations. So Bouusinesq approximation basically is the following. You see there is a rho only here, is just number. So density is assumed to be constant for mass balance, or in this case it's for momentum equation. So it's assumed in momentum equation everywhere except for buoyancy, for buoyancy term. So Bouusinesq approximation ignores, so it's incompressible. There is no compressibility of the flow except for thermal expansion or contraction of fluid, thermal. So this density is can be thermally induced, but we don't specify it here. But this system does not support sound waves because there is no d-rho dt, explicit d-rho dt term. So no sound waves. Only gravity waves. And in fact, because there is, you can retain Coriolis force, it actually has all other waves, like it can have Rossby waves, for example. So this system has basically all the waves in atmosphere that you want, except for sound waves. So that's Bouusinesq approximation. So why don't we just use it? One of the problems with that approximation, obviously, is that we assume too many things. First of all, we assume that our density, it changes with height. There is some reference change in height of reference profile, but it shouldn't be too large. But in reality, if you talk about, say, atmosphere above boundary layer, our density can decrease with height very fast. And so it's only fraction of density remains, say, in tropopause, around tropopause, or in stratosphere. Stratosphere is very small density. So we can't actually, so this approximation is not good beyond boundary layer. So this is only for boundary, only good for atmospheric boundary layer. And of course, it's good for ocean. For ocean, it's good basically everywhere. Why? Because water is very incompressible fluid. So it compresses even at very great depth. Its compressibility is very small. So Bouusinesq approximation is in fact very widely used in ocean modeling for that reason. But for atmosphere, it's not very practical beyond your boundary layer turbulence, let's say, model, like latitude simulation model. Then you can use Bouusinesq model for that. But to simulate, say, deep clouds, these big clouds, tropical cyclones, and so on, you need to move away from Bouusinesq approximation, and you still don't need sound waves. So what you do in that case? So now let's consider another filtered set of equations that don't contain sound waves, so-called anelastic approximation. This is very popular approximation for regional cloud models. Why not just, again, not use a Bouusinesq approximation? Because Bouusinesq approximation ignores variation of density in momentum equations. It says, forget about it, it's small. But obviously it is not small if you consider the whole depth of atmosphere or troposphere. Deep clouds can occupy much, it can go much higher than boundary layer top. So you need something more plausible than an elastic approximation. So you cannot ignore density, and in that approach, anelastic means like anelastic. So elastic, that basically elasticity of air. So that creates sound waves, and elastic is basically approximation without sound waves. And what an elastic approximation does, it just goes ahead to continuity equation, and instead of full derivative of rho equals to 0, it says no, only local derivative of rho equals to 0, which means that it completely ignores sound waves, only sound waves basically. Because this is what's without actually disturbing anything else, because this particular partial derivative in time, that's what makes actually sound waves. So this is what an elastic does. It says, we preserve divergence not of u, but the divergence of rho u equals to 0, so that's more precise than in a Bouusinesq approximation when it's just divergence of u equals to 0. Here it's rho u equal to 0. But this partial derivative of rho is completely eliminated. And of course, when you don't have density, you immediately lose your equation of state. So your pressure is not any longer connected to temperature and your density is not connected to temperature and pressure by equation of state. There is no equation of state. So in anelastic approximation, you lose your equation of state, similar ways in Bouusinesq approximation or incompressible equations. So this is what you retain. Now in meteorology, instead of using this equation for temperature that I showed for compressible equations, instead of that you use potential energy conservation. And for potential temperature conservation, you just use basically, if you ignore some sources of potential temperature, like heating due to radiation or heating due to latent heat release and so on, it's just written and you ignore viscosity of any sort. So it just, for simplicity, let's write it just like that, conservation of potential temperature. So that's your second equation. And now momentum equations. In momentum equations, they basically rewritten in using potential temperature in pressure gradient terms. For that, it actually can be shown that this term, 1 over rho gradient of P, actually can be written in the following form as Cp Cp potential temperature gradient of pi, where pi is not pi 3.14, but it's a so-called Exner function. First of all, let's remember what potential temperature is. Potential temperature is T temperature times P naught over P R over Cp. You know that. P naught is just reference pressure, 1000 millibars, for example. And then we basically declare this function, but it kind of reversed, P over P naught R over Cp. And it's called Exner function. So that with Exner function you write that theta equals to T divided by P. So your pressure gradient can be written like that. And now why we need that? Because we don't really have perturbation of density anymore. So we cannot compute our buoyancy using perturbation of density because we don't have it. Here we have, and by the way, yeah. So what basically we assume, so we need to use perturbation of potential temperature instead. So we assume that there is some basic state or reference profile of potential temperature, so that potential temperature equals to this reference profile plus some perturbation. Also, we assume that this is same true for pi. So pi, there is some reference profile of pi plus perturbation. And also, we replace rho everywhere, replaced by, like in Bouusinesq, spirit of Bouusinesq. But in momentum equation, we don't use reference value of density, but we use reference profile of density. So that this equation becomes like that. And now using this equation, it's kind of cool to derive buoyancy term for buoyancy term for this anelastic approximation. We basically do the same, but it's actually even easier than before. So we assume that our reference profile is in hydrostatic balance, which means that the following is true. Cp reference profile times gradient of reference profile equals to G. So that Cp, our pressure term, equals to. So if we substitute all this definition in there, and then ignore, and then cancel, as we did before, for Bouusinesq approximation, the hydrostatic state. So then we will derive, I will skip all the steps, but I will derive the final thing. That's equal to minus, actually plus. Actually it's, let's see, it's a potential temperature perturbation divided by mean times G plus plus Cp theta mean gradient of P prime. Yeah. So when it goes to the right hand side, it becomes minus G, and then G also becomes minus because gravity is looking down, gravity vector. So it becomes positive term on the right hand side. Yeah, it should be, so it's correct. All right, so this is basically what our analog of Bouusinesq, but in case of anelastic approximation. So instead of, so in Bouusinesq, we use rho prime minus over rho bar G plus 1 over rho naught. And because rho naught is a just number, we can take it inside, so we use gradient of P prime divided by rho naught. So this is in Bouusinesq approximation. So instead of that, now we have this approximation. So our buoyancy, now we ignore, so there is no density here, you see. Density only appears here. So density is given. We don't look for density because it's, you see, it's with overbar. So this is reference profile. So, and we have equation for theta, which from which we compute this perturbation from the basic state. So, so now, but the problem is, so we now can use this one, and this reference state is a function of height. The problem that if you write momentum equation with this term like this, with this term, it won't conserve energy, total energy of the system. Well, there is some total energy which is not the same as before. It's in fact different expression, but there is no conservation, so it would generate some spurious kinetic energy. So if you use term like this, it will generate kinetic energy from nowhere, from nothing. So it will be noisy, no conservation of energy. So this problem was fixed by Lipps and Helmer. So Lipps and Helmer kind of approach to anelastic approximation that basically said that these two terms should be written like the following. So this one is before, but plus Cp, you actually get it inside. This theta, you ignore its dependence on height, and you just put it inside gradient. Of course, you cannot do that in calculus because you need to add some terms, but apparently those additional terms, that would create all this inconsistency and noise. So that's why if you do it like the following approximation, which is not bad because theta does not really change very much in a say in troposphere, and in stratosphere this approximation by itself already becomes questionable because density is so low that actually even small changes in density cannot be ignored. So this system anelastic approximation is valid basically for troposphere only. In stratosphere it doesn't really doesn't work that well. Anyway, so you define this pile with head or roof or whatever, so that this guy is just Cp theta pi. And you don't actually even need to know that because you need to solve elliptic equation for this p with head anyway. So this is what your terms become, like that. And if you make it this way, so basically it looks like an elastic, like Bouusinesq approximation. Just for Bouusinesq it's different. It's p prime over. So this one is of course primes here. Not prime here, but prime here. So it looks like similar to this. So in a way, an elastic approximation very similar to Bouusinesq approximation, except you retain density dependence in your divergence of velocity. So in an elastic, this one is constant, so it can be thrown away. And you generally predict potential temperature rather than buoyancy or density, perturbation of density. That's basically the main difference. And this system also has no sound waves. So you can use much larger time steps when you solve the system. So so let's maybe I will write as a kind of I will write all approximation on one board. Actually, there is another one that I didn't cover, but I will write it anyway. Another approach to compressible that I just, in the interest of time, I will skip. So compressible system, compressible flow. It actually can be written in two forms. First is like du dt. Let's not write any Coriolis for terms on other things. Just du dt equals to minus 1 over rho gradient of p plus g. So this is a momentum equation. Then d rho dt equals to minus rho divergence of velocity, this continuity equation, and energy equation, which is cv dt dt plus p over rho divergence of u equals to 0. So this is canonical kind of compressible flow equations. Now also compressible flow equations can be written using Exner functions, and that's some models actually use that formulation. So with Exner functions, you use it's kind of more it's used almost exclusively in meteorology because it's based on potential temperature. So basically it has the following form, that du dt equals to minus cp theta gradient of pi Exner function plus g. Now instead of continuity equation, it's actually equation for Exner function, d pi dt plus r pi divided by cv, not cp, cv, divergence of u equals to 0. So instead of equation for density, you completely eliminated density, and now you use P in place of density, and then you use conservation of potential temperature. So this is also compressible equation, system of equations, but it's based on potential temperature and Exner function. So you have only 3 equations, and they're all prognostic. So there is no elliptic equation to solve here. All u, pi, and theta, all 3 variables that you don't know, you solve for them directly. Here, here I forgot to add equation of state. So here there is also plus P equals to rho RT. So here you have 4 equations and 4 unknowns. Here you have 3 unknowns and 3 equations, but this system is completely equivalent to this system. So it has no approximation whatsoever. This is also exact system. And it has sound waves. So both of them sound waves. And then this one is Bouusinesq and anelastic. So first Bouusinesq system. So Bouusinesq approximation. We have du dt equals to minus 1 over rho naught, or just let's write it like this, minus gradient of some pi, capital Pi, which is p over rho naught, plus buoyancy. Or let's write it explicitly as rho minus rho reference state divided by rho naught g. And then there is equation continuity, which is in this case just divergence of u equals to 0, and equation for buoyancy, which is just d rho dt equals to 0. Or if we write it as a rho prime, then it's equation for d rho prime plus w d rho reference state dz equals to 0. So this is Bouusinesq approach. And it's valid again only for boundary layer and for the ocean. For the ocean it's valid basically for the whole ocean. In atmosphere it's only valid approach in a very low in atmosphere, not whole, say, troposphere. So no sound waves. And then anelastic. My model, for example, is an elastic model, SAM model. It's du dt equals to minus gradient of pi plus, or minus in this case, minus theta prime over theta reference state times g. Now, instead of gradient, a divergence of u is divergence of rho u, where rho is reference state, and conservation of potential temperature. Same as in this system of compressible equations. So this one also has no sound waves. So you can run it with much longer time step than both these systems. But these two systems have their advantages. Why? Because you don't have to solve for both of those equations, because you don't have prognostic equation for pressure anymore. You have only this diagnostic equation for divergence. You need to solve elliptic equation for pressure, for this pressure or for this pressure. You need to solve elliptic equation, which can be very expensive and very difficult, especially if you have very large domain. And it's very difficult to do on parallel computers, because then it's a global equation, an elliptic equation. Remember, you did this homework with iterations. You need to iterate the whole domain. So you need to, if you use multiple processors, you need to pass all this information around. And that convergence, especially on a large domain, can be very slow. While here, everything is local. You see, it's all just local derivatives of all these variables, so you just locally solve them using finite difference method or finite volume method. And so there is no elliptic equation. So no elliptic equation to solve. And this one has elliptic equation. Have to solve elliptic equation. And that's main disadvantage of Bouusinesq or anelastic equations. It's a very elaborate structure to do that, and sometimes it takes very considerable portion of your model run just to solve elliptic equation for this kind of systems. A little addition, just after I finish this lecture, I noticed this error. Please correct it. If you make notes, of course it's going to be full, it should be full derivative. So, other than that, it's this one is also solve elliptic equation. So let's so this is all the equations on one screen.